Hello and welcome to this explainer. Today, we're going to translate the fundamental concepts of Class 9 coordinate geometry into a really clear, visual journey. Whether you're gearing up for your exams or you just want to understand the hidden mathematical grids that basically run our modern world, you are in exactly the right place. I'll be your guide as we break down these ideas step by step, making them simple, memorable, and most importantly, practically useful. Think of this agenda as our classroom blueprint for today. We'll start with Welcome to the Grid, map a room to see a real-world application, formalize the Cartesian plane, figure out how to find distances, do a little practice together, and then wrap up with a summary. Welcome to the grid. How do we locate things?
Let's kick things off with a question. Have you ever actually wondered how a map app on your phone knows exactly where you're standing? Whether you're hunting for the nearest coffee shop or scientists are launching a satellite into orbit, they aren't just guessing locations. They rely on a highly structured framework of numbers. This framework lets us use numbers to describe the exact physical location of objects in space. We call it a coordinate system. And honestly, it's the beating heart of modern navigation.
And what's wild is that this isn't just some modern tech invention. The idea of grid-based thinking goes way, way back. Thousands of years ago, the Sindhu-Saraswati civilization actually built their city streets on a precise north-south, east-west grid, spaced about 10 meters apart. Fast forward to around 628 CE, and the brilliant mathematician Brahmagupta formalized the concepts of zero and negative numbers, which, as we'll see, are totally essential for our grids. Finally, in 1637, René Descartes pulled the whole thing together. He realized that any point could be defined simply by its distance from two perpendicular axes. It was a massive leap that perfectly connected algebra and geometry.
Mapping Rienne's room, a real-world solution.
Let's bring this down from grand historical cities to a very real, very practical micro-problem. Imagine a girl named Shalini, who just moved to a new city with her family. Her brother, Rienne, is visually impaired, and figuring out a brand new bedroom is a huge challenge for him. So, Shalini used what she learned in Class 9 math to help out. She laid out a tactile grid right on his floor. By picking a starting point, which we call the origin, at the bottom left corner, she mapped out distances along the walls using a simple scale where 1 centimeter equals 1 foot. She even connected pins with thick wool so Rienne could physically feel the exact coordinates of his bed, his wardrobe, and his doors. Now that is coordinate geometry in action, literally improving someone's daily life.
The Cartesian plane, formalizing the grid.
That tactile map of Rienne's room is actually the perfect stepping stone to the formal mathematical tool you'll be drawing on your graph paper. Welcome to the Cartesian plane. Think of this as a totally flat, two-dimensional piece of paper that extends out forever. To locate anything in this space, we draw two straight, perpendicular lines. The horizontal line going left to right is the x-axis. The vertical line going up and down is the y-axis. And that exact spot where they cross right in the middle, that is our starting point. We call it the origin, and against the coordinates 0, 0. Every single measurement we take starts right there. Now, because these two axes cross each other, they slice our flat plane into 4 distinct zones, which we call quadrants. You can think of them almost like 4 different neighborhoods. Quadrant 1, up in the top right, is completely positive. If you move left from the origin, your x value becomes negative, putting you in quadrant 2. If you go straight down from there, both your x and y are negative, that's quadrant 3. And finally, the bottom right is quadrant 4, where x is positive again, but y is negative. It's a beautifully organized system, really, because the positive or negative signs tell you exactly which neighborhood a point lives in. When you see a pair of numbers inside parentheses, something like 3, 4, that is your treasure map. The rule here is so simple, but you absolutely cannot mix it up. The first number is always the x-coordinate. It tells you how many steps to walk horizontally, left or right. The second number is always the y-coordinate, telling you how many steps to climb vertically, up or down. A great trick to remember this, you have to walk across the floor before you can take the elevator up.
Finding the distance, bridging Pythagoras to the grid.
Okay, so now that we can locate points on our 2D plane, how do we measure the straight line distance between two spots, especially if they're diagonal from each other? We can't just count the grid squares when a line is slanted. But here's a brilliant little trick. If we have a slanted line connecting 2 points, let's call them A and M, we can draw a horizontal line out from A and a vertical line down from M. Where they meet, they form a perfect right-angled triangle. And since we have a right-angled triangle, we can unleash the Baudhayana Pythagoras theorem from Class 8 to solve for that slanted distance.
Let's break this down into 3 logical steps. Say we want the distance from point A to a new point D. Step 1.
Identify your data. Point A is at x equals 3, y equals 4. Point D is at x equals 7, y equals 1. Step 2. Find the shifts. Horizontally, we went from 3 to 7, which is a shift of 4 units. Vertically, we dropped from 4 to 1, which is a shift of 3 units. Step 3. Apply the Pythagoras formula. The distance squared equals 4 squared plus 3 squared. That's 16 plus 9, which is 25. Take the square root of 25, and we get exactly 5 units. Boom! You just calculated an exact diagonal distance using coordinates.
Let's practice together, applying what we've learned. All right, it's time to test these rules together. We learn best by doing, right? Here is your challenge. You're standing at point D, which has the coordinates 7, 1. You want to walk in a perfectly straight diagonal line to point M, which is at 9, 6. What is the exact mathematical distance between these 2 points? Feel free to pause the explainer right here, grab some paper, think about our 3 steps, and try to solve it yourself before we go over the answer.
Okay, let's work it out methodically. Our given data is exactly as stated. D is our first point, x1, y1. And M is our second point, x2, y2. Next, we use our distance formula, which is the square root of x2 minus x1 squared plus y2 minus y1 squared. Let's plug in those numbers. 9 minus 7 gives us a horizontal shift of 2, 6 minus 1 gives us a vertical shift of 5. Now we square them. 2 squared is 4, 5 squared is 25. Add them together. 4 plus 25 equals 29. So our final answer is the square root of 29 units. And hey, since 29 isn't a perfect square, we can just leave it exactly like that. Great job if you got that right.
Summary. Wrapping up Chapter 1.
You've done fantastic work following along with these concepts today. Let's just take a quick moment to recap the most vital takeaways you absolutely need to remember for your exams. First, the heart of the whole system is the origin, always securely located at 0, 0. Second, never forget your axes. X is the horizontal horizon, Y goes up and down vertically. Third, coordinates are strictly ordered pairs. It's always X first, then Y. Walk the floor, then take the elevator. And finally, the distance formula. Even though it looks like a big, scary algebra equation with square roots and little subscript numbers, remember the secret. It is quite literally just the Pythagorean theorem, finding the hypotenuse of a right triangle on a grid. Keep that in mind and you'll never forget it.
Today, we completely mastered the flat, two-dimensional Cartesian plane. We know how to map rooms, plot points, and calculate exact distances on paper. But as we all know, our world isn't flat. So I want to leave you with a somewhat provocative thought to chew on. If we need an x-axis and a y-axis to zero in on a location on the ground, what kind of mathematical magic do we need to add to track a drone, or maybe a bird, flying high in the 3D sky above us? Keep that curiosity alive, and we will definitely explore that in future explainers. Thanks so much for learning with me today.